trying to find out the dates and times for the makeup lectures. We had one missed lecture and 2 lectures that were used for review. I would like to make up those 3. So, the Moodle survey is on. Please do take time to indicate. We'd like to make sure that the times that are chosen are convenient for everyone. In addition, we're also, the TAs and I felt that it will be a good point for us to get some feedback also. The feedback, by the way, is anonymous, so you can feel free to give your comments, and we will definitely have a look at that and see how to incorporate going forward. So today's discussion is to complete our understanding of water filling, and also look at a suboptimal technique which causes us to think very differently from what we have been thinking so far. Because so far what we have been thinking is good channel, give more power. Now there is a sort of a counterintuitive method which says, no, let's try to equalize the power. Maybe initially your reaction would be, well, we already looked at it, it's not a good way for us to to achieve capacity. But let's look at the concept, because this concept more or less leads us into the concept of CDMA. So let me just sort of get you a little bit interested even before we talk about CDMA. So one of the things that you will find in a cellular system is that we have base stations and we have mobiles, okay? And there are very common scenarios where one mobile, let us call the mobile as MS1, the other one as MS2. Now both are communicating to the base station. And let us say both are similar mobiles, that is, both can output the same transmit power. Now if both are transmitting at maximum power, then what is the situation at the base station? At the base station, I am hearing mobile station 1 very loud because it is coming in with full power and the losses are not much. Okay. Mobile station 2 is somewhat faint because the mobile station is far away and it is suffering a significant amount of path loss. Okay. So this is the scenario. Mobile station 1 very close to the base station, mobile station 2 far away, both are transmitting with the full power. Okay. Now under what condition will mobile station 1 interfere with the detection of mobile station 2? Under what condition? Under what condition? So basically within a cell, we assume that the resources used are orthogonal. If mobile station 1 is on time slot number 1, mobile station 2 is on time slot number 2, it does not matter at all, because when I am detecting time slot number 1, I am hearing only mobile station 1, time slot 2. If they are on different frequencies which are completely orthogonal, again no impact. However, if there is a scenario of non-orthogonality, that loss of orthogonality, okay, one such scenario that can happen is, let us say they were on adjacent channels. So this at the base station, mobile station 1 is like this, the second signal is much weaker. So when I try to filter out mobile station 2, I will get a significant portion of mobile station number 1. So this is the filter that is applied, and you can see a significant portion of green is leaking in, and therefore will cause me disturbance. Okay. So loss of orthogonality, very, very important when we talk about different users, and one such situation arises in CDMA, because in CDMA both are using the same frequency, and if for any reason there is a loss of orthogonality, then they will interfere with each other. So for this purpose, there is a requirement in CDMA which says mobile station, all the mobile stations ideally should be received at the same received power. That means even under loss of orthogonality, how much degradation 1 causes to 2, 2 will cause to 1. Okay. It is not that 2 will cause a lot of 1 will cause a lot of degradation to 2 and therefore wipe out my ability to detect. So this problem is called, particularly in the context of it's called the near far problem. The near end user can affect the ability to detect the far end user, and you have to take care of this when the users are in some way have lost orthogonality with respect to each other. It's a very, very important concept. Okay. Now, how do you do near far? How do you address the near far? You ask the nearby mobile to say, okay, reduce your power. Okay, you've got good channel, reduce your power. What do you ask the far end user? Okay, your channel is weak, boost your power. So what are you trying to do? You're trying to compensate. Good channel guy, you say, okay, reduce your power. Bad channel guy, but that's counterintuitive to capacity, because capacity, what do you say? Hey, near end guy, you transmit with more power because you can get more capacity. So there is a sort of a contradictory. But CDMA requires you to do near far, address it. Okay, so we will talk about what are some of the aspects. But before that, a quick review of the capacity. Channel state information at the transmitter, instantaneous and perfect. Notice that we now have the ability to do power allocation. So previously the SNR depended on the average SNR, which is the SNR that you would see in an AWGN channel, modified by the fading coefficient. But now you don't have to live with that SNR, you can modify it, and the modification is through the power allocation P gamma of over P bar. Now P gamma over P bar, I want you to take a moment to do that. So this can be greater than 1. If it is greater than 1, you are boosting the power of that particular SNR, boosting. Of course, it can be equal to 1, less than equal to 1, you are not modifying anything. Less than 1, what we are doing is we are doing a power reduction. So SNR can be either boosted or reduced artificially because of through power allocation. So the modified SNR with the power allocation, now the channel does not know, I mean when it goes over the channel, it does not know whether you did power allocation or not. All it knows is a signal was launched and this is how I'm going to receive it. So the SNR that you're going to receive at the other end is now modified, because the instantaneous SNR gamma got modified by the power allocation that you did, and so you need to keep in mind that you have now artificially modified the SNR. The channel, the fading channel gave you an instantaneous SNR, and you have modified it to for whatever under whatever constraint that you have chosen. So CSIT environment requires us to keep in mind that we have modified the SNR over the channel. Okay. That's a very, very important point. Now, what if I use this allocation? P of gamma by P bar equal to 1 for all values of gamma. What does that indicate? I'm doing uniform power allocation. I'm not changing the SNR at all. I'm not changing whatever was the original SNR. So basically, this is uniform power allocation. Uniform power allocation. But that is not the idea. The idea is to actually allocate differentiated power to the different SNRs so that you can maximize the capacity. Okay, so the constrained capacity problem, as we had written down yesterday, is we want to optimize the capacity with the modified SNR under the constraint that your total power allocation has to be normalized. It cannot exceed the average power. So this is the average power constraint. So this is the statement of the problem. One way to achieve the, assuming that the channel has perfect knowledge at the transmitter, we said that the way you would achieve the capacity would be to look at different combinations of encoders and decoders which will work for different SNRs, but it's not this SNR that's going to be seen on the channel, it is going to be this SNR modified by the power allocation that I'm going to do, that's going to be seen on the channel. Okay? So very important that this picture tells us how to achieve capacity once you know the instantaneous SNR and you have designed this system of encoders and decoders. But the key question that remained and which we addressed in the last class was, how do we find out the power allocation? That's the important question. Okay? What did we write down? We wrote down a objective function in terms of a Lagrangian, and we differentiated and set this equal to 0. Very rightly, several questions arose after the lecture saying that under this condition, you cannot say that the integrand has to be equal to 0, because the integrand, because you're taking the integral is equal to 0, so you can have the integrand can take positive and negative values, which when integrated can actually go to 0. So yes, that is a correct statement. The correct way to interpret this equation after differentiation is that you have to satisfy this condition equal to 0, and a sufficient condition that will satisfy that is setting the integrand equal to 0. Okay. So that is the one step. It is not a necessary condition, or at least from here we cannot deduce that it's a necessary condition. However, one of the TAs, Biswajit, actually pointed out that if you look at Say and Vishwanath, the optimum power allocation has been derived not for the continuous case, because what we are doing is for the continuous case. Optimum power allocation has been derived for the discrete case. Okay, discrete case. So that means you have a finite number of SNRs with probability, and you're trying to find out what's the optimum power allocation. And I would definitely encourage you to see this, where it is shown that when you under this condition, it's not just necessary, it's not just sufficient, it is necessary and sufficient, and it maps to the same condition that we have obtained. But from our discussion, please be the correct way to interpret this is that there is a sufficient condition which achieves the required, setting the derivative equal to 0, and that also will lead us to an optimal solution. Okay, very important. Our interpretation of the power allocation, we explained it in terms of water filling. If you think of this as a bowl, the 1 over SNR graph as a bowl, and the line 1 over gamma naught as a water level, then the depth of water, that's the amount of power that you will allocate to that particular channel. So the power allocation algorithm is going to be the difference between the water level and the level of the bottom of the vessel. So, and of course, you will not allocate negative power. So this is a quantity that is strictly non-negative, and if the SNR goes below the threshold, then in fact you do not allocate power. That's the same as saying no transmission occurs. So no transmission for very bad channels, and the power allocation done as per the water filling. So the conclusion is that if I have a narrowband system, this narrowband system will experience flat fading. At any given point in time, the SNR will go up or down. My goal is to adjust the power transmission, power allocation, so that I get maximum capacity. So how do I do that? Basically, look at the SNR and quantize it. And for each of these SNRs, what we would do is go back to the diagram where we saw a family of encoders, decoders, and also be able to allocate power. The allocation of power would be based on the water filling algorithm, 1 by gamma naught by 1 over gamma j. And of course, if the SNR goes below the threshold, that means there is no transmission. So this would be the way that we would view that. So at any given point in time, we are transmitting the information with the correct encoding, decoding, with the correct power level to get the maximum out of the capacity. So over a period of time, if you look at a channel with time varying capacity, then we have been able to achieve the best possible with the information at the transmitter. Okay. I would like to just spend a few minutes on the extension of this problem. What we are saying is we are going to look at a case where it's a wideband system, which means that frequency selective fading. However, we have made the assumption that it is time flat. So the steps that we are doing, and I would like to just highlight that. So the steps that we are doing are, we are going to first divide the channel into subbands. Channel is divided into subbands of bandwidth B. Subbands of bandwidth B, where B is much less than coherence bandwidth, and that would mean that I can safely make the assumption of frequency flat fading for each subband. The whole signal, of course, is seeing frequency selective fading, but I have divided it into subbands which are experiencing flat fading. Okay. For each of these subbands, the corresponding channel response, H of j omega I'm going to call this as Hj. J is the index of the subband, and it is the same for the entire subband. J is the subband index. Okay, so what we are saying, we have a wideband signal. Wideband signal is going to experience some frequency selective fading. So the wideband signal itself is something like this, but I'm going to divide it into small bands of bandwidth B, and this particular band is experiencing frequency flat fading. Okay. So like that, I have divided my entire signal into subbands. So now the capacity for a frequency selective fading channel, we wrote this down without the full description, so I thought I would make it a point to write it down in today's lecture for completeness. Capacity is equal to summation max over Pj. Okay. Now, is this a probabilistic power allocation? Is this a probabilistic power allocation, or is it deterministic power allocation? Basically, I have to maximize the power. Keep in mind that this is a time flat channel, so that means nothing is changing. So which means that once I know the frequency response of the channel, there is no probabilistic element to it. I just need to find out the power allocation for corresponding to each of those channel gains. So it's maximum over Pj summation Pj less than or equal to P. There's a total power that I have for the transmission of the given signal, and I'm allocating it to different subbands, different power to different subbands. So the total power, not on an average level, instantaneously also has to be less than or equal to P. So notice that it's a slightly different formulation than the previous case, but it's good for us to write it down. So the capacity itself will be equal to B. There are several of these subchannels. Logarithm base 2 1 plus mod h of j squared, that's the gain of the channel. I'm going to modify it by Pj divided by P, Pj divided by P, that's the scale factor that we are going to apply, and basically the signal to noise ratio or gamma after that. Mod hk is already indicating that. Let me see, mod hk times the, okay, gamma is fine, okay. So the optimum power allocation, as in the earlier case, it will be through some method of approach of water filling. Optimum power allocation, Pj divided by P is given by 1 by gamma naught by 1 minus gamma j. Yeah, let me just write this as gamma j. Yeah, go ahead. No, because that is the channel gain.
This frequency response comes because of that multiple parts, right? So
no, wait, okay. The question is, how do you what portion comes from the signal and what portion comes from the channel? Okay, think of it like this. I transmit a signal of a certain bandwidth. It is going through a normalized channel with certain gains. Okay. So Hj you dissociate from the transmitted signal power. So basically there is an SNR with which I can transmit this signal. That can be written as the signal power with a certain PS. So that would be the signal. This multiplied by mod Hj squared is what the channel will produce. So PS multiplied by mod Hj squared will be the gain that this signal will produce. Now, over and above that, I may choose to do power allocation. Okay. So, the basic signal power multiplied by the channel gain multiplied by any power allocation that I have done. So, that will be the resultant SNR. So, PS we can assume is constant for all the subbands. Each of the subband will see a different gain based on Hj, and then I will do power allocation based on that. Okay. Yeah, good question. So, always clarify that. So, basically if I treat, so how will gamma j be defined? This divided by Pn will be gamma j. Okay. So, and based on gamma j, I will then decide to either allocate more power or less power, and that will be the resultant signal. Okay. So, and of course, this will be equal to 0. This is for gamma j greater than or equal to gamma naught, for gamma j less than gamma naught. So, this is the optimum power allocation, and this is how we have achieved the capacity. Okay. Now, let us go back to the previous graph and now see how we want to achieve capacity. So, supposing the channel has got the channel gains which have the, let us say just as an illustrative case, equal, all of them must have equal bandwidth. So, I first divide my, my channel into segments of bandwidth B. A bad channel, next one is good, next one is medium, another not so good channel, and then okay, another good channel. So, basically this is what the channel response looks like. So, I first have to, I am going to do a channel inversion. So, the same boundaries. Now, I am going to take 1 over gamma j. So, this corresponds to gamma 1, gamma 2, gamma 3, gamma 4, gamma 5. Notice it is the whatever the signal SNR is modified by mod Hj squared. Okay. So, I am going to take the reciprocal. So, this is 1 over gamma 1, 1 over gamma 1. This is 1 over gamma 2, 1 over gamma 2, 1 over gamma 3, 1 over gamma 4, and of course 1 over gamma 5 is also a good channel. So, now water filling basically says find that level which is going to indicate the water filling point, so that it will satisfy the average power constraint, the required power constraint. So, this channel no transmission, this channel no transmission, because they are above the power allocated for this channel will be given by this. So, this will be P2 divided by P, that is the power allocation here, and this one is going to be P3 divided by P, and P5 divided by P, that is the power allocation, P5 divided by P, and some channels are not transmitted, and this is how we achieve capacity for a wideband signal. Okay. Maybe one more comment before we move away from this discussion. So, supposing you had this channel, supposing you had a channel of this type where you had very bad channel conditions for one part, good channel conditions next, and then medium, poor, very good, and so on. Okay. Now, what would have happened had I transmitted a single carrier signal through this? If I had transmitted a single carrier system, this is a single carrier system, what would have happened? This portion would have been severely affected, distorted. See something like this, something like this. So, you can see that my signal is going to be severely distorted, okay, severely distorted. Now, of course, I can recover the original signal by equalization. So I can go back from here to this point via equalization. So my ability to detect the signal, a wideband signal which has gone through frequency selective fading, is not the issue. But now the question is, how do I achieve capacity? Because what it says is, hey, in this portion alone, I don't transmit any information, because that's very bad channel on this part. Only transmit in these things. And they say, no, I can't do that, because I cannot create nulls in my transmitted spectrum, because it's a single carrier system. So at most I can do some shaping of my spectrum. So for example, you can do things like, you can shape your spectrum, but I cannot create nulls for you. So that is a important ability. So if you tell me that I have to work with a single carrier system, I am going to say the following. Equalization I can do. I can recover the signal. Okay, it may be complex, because depends on the complexity may be high, but that's I can recover the signal. But what about capacity? Now it is difficult to achieve capacity, because I cannot change the power allocated to different portions or different segments, frequency segments of the spectrum. So difficult to achieve capacity. Okay, so what I will have to do, either boost the whole signal or reduce the whole signal, and there's no way of matching the transmitted signal perfectly to this information. Okay, however, if I could transmit these as individual signals, basically multi-carrier modulation. So this is for a single carrier system, single carrier. Now on the other hand, had we transmitted a multi-carrier system, so this is some bandwidth B, let's call it as B prime, and this B prime is equal to n times B. So basically the multi-carrier has got n carriers of bandwidth B. So each of these subcarriers, so subcarrier bandwidth is equal to B. Now for each of the subcarrier, is equalization needed? Subcarrier equalization probably is not needed, and even if it is needed, it's going to be very simple. Okay, so either not required or it is going to be simple, low complexity. Okay, so equalization is not an issue. Now what about capacity? Absolutely no problem, because I can do power allocation. I can allot enough amount of power. Now what is the use of allotting power for a particular sub-channel? That means that channel is going to see a better SNR. Now why would you do that? If you want to transmit more information on that. So it's always, along with power allocation, we do something called bit allocation. What modulation scheme you are going to use for that particular system? So bit allocation is another way of saying the modulation method. So is it going to be 16 QAM? Then I have 4 bits per symbol. So you boost the power and say, okay, transmit 4 bits on this sub-channel. On this sub-channel, okay, just do BPSK, 1 bit per symbol. So 4 bits per symbol, or you could go to 64 QAM, which would be 64 QAM will be 6. So basically, you will always hear the term power allocation and bit allocation. So please don't get confused, say, oh, there's something which we have not looked at. The only reason you would allocate more power is to send more information. And how would you send more information? You would send it by transmitting more bits per symbol. Okay? And this is precisely the reason why a multi-carrier system can achieve capacity when a single carrier system cannot achieve. Because what can you do with a single carrier system? You either choose 16 QAM for the whole signal, or 64 QAM. 64 QAM maybe may end up having bit errors. Whereas this particular case, when you have multi-carrier modulation, that particular subcarrier, because it's got sufficient SNR to support 64 QAM, you can send 6 bits per symbol. Some other subcarrier has got less SNR, you send 4 bits per symbol. So that's how you achieve the capacity. So think along the times of, okay, I have to achieve capacity over a wide range of frequencies. How do I achieve it? Achieve it by dividing it up into small chunks. It simplifies equalization. It helps me do allocation of power through water filling. Once I have that, then I can send more information or less information based on the SNR that is currently supported. So more or less, if you say that you want to achieve capacity for a wide band, achieve capacity or maximize capacity over wide bandwidth, it almost forces you to go to multi-carrier modulation. Okay? And what we know multi-carrier modulation is as OFDM. So OFDM comes in with a very natural advantage, saying that, okay, this is the scheme that will help me achieve capacity. This is the scheme that will reduce the complexity of the equalizer. Of course, there must be some penalty that you pay. We will look at that as well. So we have already seen the motivation for OFDM, but let us keep that in the background. We're going to study OFDM, but before that, as a good engineer, you look at the solution and say, well, you know what? This system achieving capacity is actually quite complex, because first you have to solve the power allocation problem. Then on top of that, you have to design this bank of encoders and decoders, and you have to keep feeding back. Okay? So the question that you ask as a good engineer, saying that, okay, CSIT is a very valuable tool. Make that assumption of CSIT. Okay? But I want to simplify my design. Simplify the design of the system. Okay, now you ask the question, how much you want to simplify? I said, the answer comes back, I want to have one encoder, one decoder. And I say, okay, now you have to be realistic. You're trying to achieve capacity here. You have to be, you've just now seen that, how difficult it was to achieve capacity. So again, the notion that comes about is the following. The notion of channel inversion. So when the channel is bad, boost it. When the channel is good, sort of pull it down so that you sort of get something which is on average the same. Okay? So what is the, how would we represent this? So channel inversion says the power allocation P of gamma by P bar is going to be such that it is sigma divided by gamma. Sigma is some constant, don't think of it as variance or anything. Just some constant divided by SNR. Okay? So now multiply the power allocation with the SNR, what do you get? Sigma. So under all conditions, what is the SNR? Sigma. When you have only one SNR, how many encoders do you need? A decoder do you need? Only one. Okay? But the question is this even a system that's going to give any benefit at all? So let's take a look at it. Okay? So basically, you can understand that this is doing perfect channel inversion, because what it says is by doing power allocation, so this basically makes it look like, makes channel looks like an AWGN channel. Channel looks like AWGN channel. AWGN with SNR equal to sigma. Okay, it's like a fixed SNR. Okay, it's a very interesting concept. It's channel inversion. This is what CDMA systems will do to solve the near far problem, because they want both the signals to be all signals to be received at the same power. So now, what is the power constraint? So the power constraint that we now have to satisfy. There is an average power constraint because you're going to boost the power. So this basically says integral of sigma by gamma, that's P gamma by P bar, F gamma of gamma, D gamma equal to 1, integral 0 to infinity. Okay? Now, this is a interesting expression, because sigma is a constant. If I pull that out, it's integral 0 to infinity 1 over gamma F gamma of gamma D gamma. this has to be equal to 1. What is this integral? It is expected value of 1 over SNR. Okay, very interesting. Okay, so basically we are interested in 1 over SNR. Okay, because that is going to. So, and what is your AWGN level or this constant SNR level? That will be equal to 1 divided by expected value of 1 over gamma. So this is channel inversion. So if you now were to ask what is the capacity of a fading channel under channel inversion, capacity of fading channel under channel inversion. Basically you are looking for a equivalent computation of ergodic capacity. C is equal to B times logarithm base 2 of what? 1 plus sigma. It looks like an AWGN channel, right? So there's no ergodic thing, nothing came into that picture. This is equal to B times logarithm base 2 of 1 plus 1 over expected value of 1 over SNR, and that's a very interesting expression. Because what it says is if you can do channel inversion for me, then all I need is one encoder, one decoder, and it will achieve the capacity of an AWGN channel which has an SNR 1 over expected value of 1 over gamma. Okay, so it's a very interesting scheme. We just want to know how good this method is and whether we can exploit it to our advantage. Okay. So let's take a look and see if we can revisit our example. Example, the bandwidth is 30 kilohertz. I have 3 SNRs, gamma 1, gamma 2, gamma 3. This is 0.833. Next one is 83.33. This one is 333.33. And the probabilities are 0.1, 0.5 and 0.4. Okay. So I want to do channel inversion. Channel inversion says first find the sigma, expected value of 1 over gamma. So this will be 0.1 divided by 0.833 multiplied by 0.5 divided by 83.33 plus 0.4 divided by 333.33. This comes out to be, please verify, 0.1272. Again, I want you to verify that. And now the important thing, what is the capacity under channel inversion? So this would be 30 kilohertz ln divided by ln 2 natural logarithm of 1 plus 1 over 0.1272, and that comes out to be 94.43 kbps. Okay, if you were to put a smiley, you were to put a bad smiley, sad smiley, because didn't really achieve the gave you a disappointing answer. It's like, okay. Now, on the other hand, had we did capacity of an AWGN channel with the same average SNR, we know that the AWGN channel with the same average SNR achieved 223.8 kbps, and under water filling with lot of complexity, we actually have achieved 200.8 kbps. Okay. Now, never give up if it doesn't work the first time. Now you say, well, you know what? What did we try to do? You try to invert the channel under all conditions. Say, no, I think I know from channel capacity that it's not worth spending your resources on very bad channel conditions. So we now say that, okay, we're going to do something called a modified channel inversion, or what is called a truncated channel inversion. So I'm not going to invert all the channels. I'm going to say, okay, when it's very bad, ignore. Only the reasonable channels I want to do channel inversion. So that's called truncated channel inversion. Truncated channel inversion. because you do not want to mess with the very bad channel conditions. So, basically what we are saying is P of gamma divided by P bar is going to be channel inversion sigma by only when it is greater than or equal to some threshold and is equal to 0 otherwise. Okay, so, no power allocation under bad channel conditions. Okay, this is like you are trying to take some benefit or intuition from water filling. Okay, and of course, this will result in outage. So, probability of outage is when probability that gamma less than gamma naught. So, that you cannot avoid, because you are not you are going to basically not deal with those channel conditions. Okay. So, now we have to find out what is my sigma level. So, it is no longer expected value of 1 over gamma, but it is a modified expectation with only when it is above gamma naught. So, I am going to write expectation subscript gamma naught to tell you that only over. So, this is defined as integral gamma naught to infinity 1 over gamma p gamma of gamma d gamma. Okay, so, basically it is like expected value, but I am going to do it only over the region of interest. Okay. So, the capacity with channel inversion plus outage, you are going to understand that there are going to be some channels under which we cannot transmit information. So, this is going to be you maximize over all possible thresholds gamma naught, you decide where you want to set the threshold, and beyond that you will do the channel inversion b times logarithm base 2 1 plus 1 over this modified expectation. Okay. And this is basically the channel that you will get, but make sure that we also multiply it by probability that gamma greater than or equal to gamma naught. In other words, you must do 1 minus probability of outage, because otherwise because this is like a constant for all time, but you know that certain periods of time there will not be any transmission because you have not done the channel equalization. So, basically let us assume that gamma 1 is omitted in the example. Gamma 1 is omitted, and all we have is the gamma 2 and gamma 3. So, expected value of gamma naught by 1 by gamma is going to be 0.5 divided by 83.33 plus 0.4 divided by 333.3. This gives us approximately 7.2 into 10 power minus 3, and the capacity will be 30,000 log base 2 of 1 plus 1 divided by 7.2 into 10 power minus 3 multiplied by 0.9, 1 minus probability of outage. This comes out to be very surprised, 192.46 kbps. That is not bad. Okay. It actually is pretty close to your water filling actually. Okay. So, what does it say? This channel inversion. So, sometimes you have to be quite willing to look at the options. Of course, this is for a particular channel with only 3 states. So, what happens in a but the good thing is this has much less complexity, because all it requires is the ability to have a single transmitter, single receiver, single encoder, single decoder, and your water filling is very straightforward. You are trying to achieve something which looks like an AWGN channel. Okay. So, there are some practical challenges with trying to do channel inversion, because if you have a channel that is varying very fast, then inverting that channel is a little bit difficult, but nevertheless, at least as a concept, this is a very powerful method. So, the key points to take away from here is we have talked about channel capacity, we talked about the various aspects that affect channel capacity, how the desire to achieve the maximum capacity leads us to multi-carrier modulation and to water filling. Okay. On the other hand, this channel inversion method sort of tells you, hey, don't try to optimize on a subband level, treat it, equalize the channel, and you can do quite well, and and also be able to work with reduced complexity. Okay. Now, last comment. If I now have a wideband signal, which means that I am going to have frequency selective fading. Previously, we assumed that it was time flat, but now we are going to say it's time selective as well. Okay, there is a wideband signal, frequency selective fading, so which means that at a given point in time, I'm going to look at the water filling in frequency. Okay, so this delay dimension, instead of tau, now I have moved it over to, so if I were to do water filling, so this is across time. So at this time instant, my water filling is going to be some water filling I'm going to do at this particular time instant. Okay, but that's not going to be the optimum solution for forever. So at some later point in time, I may be doing a completely different water filling. So lot of signal in the first branch, maybe the next not so much signal in the third one, medium, very less. So basically, connect the corresponding points. And you can see that the water filling is not a single water filling, but you are constantly adjusting the water filling as time progresses. So for each time snapshot, you are doing the water filling. Okay, and you are doing water filling over frequency as well, because it's a wideband signal which has got frequency selective fading. So if this is the time axis, so this is water filling over frequency to achieve maximum capacity across the different subbands, and across time, because your frequency response of the channel is changing, and therefore your subband, you're still subband, because subband is what will achieve capacity. So basically multi-carrier techniques, but you keep adjusting the power level as you go. So what are you doing? You're doing power and bit allocation. Okay, that I'm sure you should be able to interpret that, power and bit allocation over time and frequency. Over time and frequency is the complete way that you would achieve for a wideband signal that is time varying or passing through a time varying channel. You would do the power allocation, and this is exactly what 4G does. LTE system, multi-carrier, 1024 carriers. Each carrier, as a function of time, you adjust the power and the bit allocation, and the next time instant you keep changing it. So basically, this is how we achieve capacity in the cellular system. Okay, any questions? Okay, if not, I would like to just sort of sow the seeds for CDMA systems, and then we pick it up from there. CDMA systems, actually originally known as spread spectrum systems, not as CDMA, spread spectrum systems, because CDMA does not necessarily mean spread spectrum, because you can get spread spectrum in other ways also. Frequency hopping is also a way to get spread spectrum. CDMA is one way to get spread spectrum. So CDMA not equal to spread spectrum. Okay, so spread spectrum systems actually originate from the military. So originate from the military because they have a requirement which says that the enemy should not be able to detect my signal, and there is no way you can hide a signal if your noise floor is here and what you have transmitted is sitting up like this. Okay, this will get detected. So the only way that you can expect the enemy not to be able to detect your signal, two ways. One is you keep changing the center frequency. So if this is the frequency, and no, this is frequency and this is time, this is time. Okay. So, you transmit at one frequency at this time instant, next time you jump to another frequency, a third frequency, basically this is frequency hopping, frequency hopping. So, unless the enemy knows your hopping pattern or has got a very sophisticated receiver that can track your hopping pattern, it would be difficult. It is a difficult problem. But what can be, how you can make it even more difficult is if you can make your signal look like noise. So, this is noise and your signal is actually looks like noise. So, there is no way the somebody who is receiving the signal. So, how do I make this signal into something that looks like noise? And that is the basic tenet of spread spectrum. And but what we are looking at is how does this concept, which actually originated for the military to make the spectrum in a way that it is difficult to detect, how is that going to make a difference for a cellular system? And that is where, if you remember one of the early slides that we had discussed, says that basically the spread spectrum portion is the part where you take a narrowband signal and make it wideband, you spread it. Now, the key point is we have multiple users. It is not one signal that you are trying to hide. You actually have multiple users, multiple signals, and that is where you have the orange and the pink, and then eventually you have to recover these signals. So, our goal would be to see what elements of a spread spectrum system are important for us in the context of a cellular context, and how do we spread, what are the assumptions that we are making, when do this orange and the pink signal lose orthogonality. Basically, if they are perfectly orthogonal, remember we said that they will not interfere with each other, but if they lose orthogonality, and what is loss of orthogonality in a spread spectrum system, all of those are the elements that we are going to study. So, as a preparation for that, I would like to request you to, whatever spread spectrum you have studied as part of digital communications, please review that. We will just pick it up from there and quickly move into the cellular system, which is built on the spread spectrum as the underlying modulation method. Okay, that will be starting from the next lecture. Thank you.